Welcome to This Explainer. Today, we're tracing an absolutely incredible journey. We're going to look at how a single human-made object launched into the literal void back in 1957 snowballed into this massive, invisible infrastructure that powers, well, pretty much every aspect of our modern lives.
It's something we totally take for granted every time we check the weather, sync our bank accounts, or just use the maps on our phones. We are entirely dependent on this invisible web of signals just raining down from space. But how exactly did humanity cross that threshold and enter the space age in the first place? Okay, let's dive into this.
Section 1. Dawn of the Space Age. Just picture the anticipation of reaching beyond our atmosphere for the very first time. It gives you chills, right? And the speed of that early progression is just fascinating. Sputnik 1, launched by the Soviet Union on October 4th, 1957, achieved the seemingly impossible. It became the very first human-made object to successfully orbit Earth. Now, it was a relatively simple metal sphere, mostly just transmitting a basic radio pulse. But then, literally just 1 year later, in 1958, the United States launched Explorer 1. And this wasn't just a milestone to simply match orbits. No, Explorer 1 carried a cosmic ray detector designed by Dr. James Van Allen. As it orbited, the instrument's Geiger counter actually registered zero radiation at certain high altitudes. Now, at first glance, you might think, oh, it's a malfunction. But it wasn't. It was the discovery of immense belts of trapped radiation around the Earth, what we now call the Van Allen radiation belts. The leap from merely trying to survive orbit to actively studying this intense, unseen space environment happened almost overnight. But going back just a step, we have to recognize that the launch of Sputnik 1 officially marked the beginning of the space age. Its true impact, though, was how it fundamentally changed the global trajectory of engineering and science. I mean, this single moment forced a worldwide paradigm shift. It wasn't just a cool technological demonstration. It catalyzed massive, unprecedented investments in education, physics, and aerospace engineering. The conceptual idea of space went from a realm of pure science fiction straight into a tangible, highly strategic domain. Humanity suddenly woke up and realized that the ultimate high ground wasn't a mountaintop anymore. It was low Earth orbit. Section 2. Rapid Expansion and Tech. So the momentum accelerated dramatically through the following decades. Let's trace this evolution real quick. In the 1960s, the primary focus was on proving utility. We saw the very first developments for active communication and weather forecasting. Think of things like the TIROS-1 satellite, which beamed back the absolute first television footage of Earth's weather patterns. This proved satellites could be incredibly practical, a real game changer. As we moved into the 1970s, the architecture expanded heavily into scientific research and dedicated military purposes. The big engineering challenge here shifted toward longevity and stabilization, because early satellites kind of tumbled unpredictably, but the introduction of three-axis stabilization meant spacecraft could point precisely at the Earth or out into the cosmos. Pushing into the 1980s, widespread television broadcasting and highly detailed Earth observation emerged. Over the course of just these 3 decades, we shifted from utilizing these bulky old-school vacuum tube electronics to actually incorporating integrated circuits and microprocessors. Basically, satellites rapidly became smaller, exponentially more powerful, and crucially reliable enough to function in the harsh, irradiated vacuum of space for years on end.
Section 3. The Global Navigation Revolution. Now, the 1980s represent the exact era where this high-level space technology truly began to intersect with everyday human life. And this brilliantly illustrates the shift we made. We moved away from isolated, one-off science experiments and classified platforms right toward a globally connected commercial network. This whole transition involved creating standardized satellite buses, which are essentially the core structural and power components, and that drastically reduced manufacturing costs. Consequently, we saw the rapid deployment of global communication networks handling massive volumes of data, live television broadcasting beamed instantaneously across oceans, and continuous high-resolution Earth observation. The infrastructure required ground stations and satellite constellations to operate in complete synchronization. It practically shrunk the world and started binding the entire global economy together. Of all those advancements, though, the development of GPS satellites really stands out as a turning point that completely revolutionized navigation around the world. The technical elegance required to make GPS work is honestly staggering. It relies on a constellation of satellites, and each one is carrying incredibly precise atomic clocks. Right now, your smartphone receiver calculates your exact position on Earth by measuring the impossibly slight time delays of signals arriving from at least 4 of these different satellites. It triangulates your position down to the meter. And because these satellites are moving so incredibly fast and they're situated deeper in Earth's gravity well, engineers literally have to factor in Albert Einstein's theories of relativity to prevent the clocks from drifting. That system, which currently tells you when to turn left or guides massive global shipping fleets safely into harbor, traces its roots directly back to this era. It's a mathematical and engineering marvel that we casually rely on every single day.
Section 4. Our modern satellite network. Thousands. Today, there are literally thousands of satellites currently orbiting our planet. The contrast is just profound, isn't it? We went from a single metal sphere in 1957 to a bustling orbital highway. This exponential increase is largely driven by a massive reduction in launch costs and the extreme miniaturization of technology. Instead of building these massive billion-dollar spacecraft the size of a school bus, commercial entities and universities are now launching CubeSats. These are satellites sometimes no bigger than a shoebox, equipped with off-the-shelf commercial electronics. This democratization of space access is exactly why the number of active satellites has absolutely skyrocketed in recent years.
So, the crucial point is that this vast, invisible infrastructure orbiting our planet functions as an immensely complex ecosystem. Navigating low Earth orbit today actually requires sophisticated collision avoidance algorithms and constant tracking. I mean, you have to ensure these thousands of machines don't collide at thousands of miles per hour. This ecosystem is actively supporting real-time global communication, highly accurate weather monitoring, pinpoint navigation, and groundbreaking scientific research. Satellites monitor crop yields, track deforestation, and manage disaster relief efforts. They also act as the essential communication relays for our deep space missions. We've essentially built a vital, interconnected digital nervous system for Earth, suspended hundreds of miles above our heads.
As the source text so perfectly summarizes, the history of satellites reflects humanity's remarkable progress in science, technology, and space exploration. It's a true testament to what's possible when we relentlessly push the boundaries of physics, engineering, and our own imagination to solve incredibly complex problems on a global scale. Which leaves us with a final thought to ponder as we wrap up this explainer. If we went from one single satellite to a vast, highly coordinated network of thousands in just a few short decades, what does this remarkable progress mean for the very future of space exploration? As technology continues to miniaturize and access to orbit becomes even easier, where exactly will this invisible infrastructure take us just a few decades from now?